Hi everybody. For this series, we're going to study digital systems. Actually, I got a book here by James E. Palmer and David E. Perman. I actually used this book um, to study for the program in microelectronics manufacturing. That's for my master degree at Rochester Institute of Technology. And actually, Professor Perman is the editor of the book. That's he actually running the course that I took. And this one is about a professor of electrical engineering at Rochester Institute of Technology, or RT. And he assigned some work, so that's why I bring up these topics to put on the YouTube. And here's some of my work when I study. So we have many assignments. Okay, let's get started. Basically, you're probably familiar with the digital system already, but this one is seemed to be a newer techniques to work on our digital system. And we're going to start from the introduction and get into deeper and deeper later on. So be follow. For this series, I have a total of 7 pages. Starting with page number 1. We start with the NAND Gate. So the purpose of this lecture is that just give you the guide for you to be familiar with the mixed logic. So what does it mean, mixed logic? For example, in this case, it means that we're going to talk about high true and low true. Okay, and I will explain later on. And for this part, we're going to use the NAND hardware to implement OR gate or AND gate. Okay, so you probably know straightforward about the AND gate and the OR gate and etc. of digital gates already. So let's take a look at the NAND gate. This is the truth table for the NAND gate. So what I mean for HT is the high true, and we also have for low true, or LT by short. For LT, that means you need to inverse all the logic. For example, if you have the logic 1 for low true, that logic going to be 0. Or if you have the high true logic to be 1, to be 1 for low true logic going to be 0. Okay, so that's the agreement. For NAND gate, you have a 3 input, so that means you have 2 to the 8, to the 3rd combinations. That means you have For input A, that's going to be your low, 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 and high, 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 high. Or sometimes you put low as 0 and high as 1, right? And this is your B input, and this is your C input. And for the NAND gate, for high true output, that means your output going to be sorry, this is the NAND gate. You know that your output going to be low when 3 of your inputs are high. So that's why I have here for input A, B, C to be high. Let's give the output to be low. That's for your NAND gate. Okay, so we start from here. That's the basic one. And then now let's take a look at the mixed logic as the design tool. From NAND hardware gate, if you play around with this a little bit in the term of high true or low true, for this case, if you assign input to be high true, sorry, you're going to have your input like this from the truth table. And if I assign output to be low true or LT, that means it's going to be inverse, or it's going to be opposite of your NAND gate truth table. This one. Okay, from this table. And now let's take a look at if your output is the low true or LT. That means from input ABC 1 1 1, this turned out to be your output turned out to be 1, because you put this one as the low true, and the rest going to be 0. So that's the opposite of the NAND gate truth table, when you have your input is the high true and your output also high true. Okay. And if you notice, this one seem to be the truth table give you the AND gate, right? Because for input ABC to be 1 1 1, that's give you 1. Or your output is going to be 1 if only your input are all 1, and the rest going to be 0. Okay, so this means you can implement your AND gate by using the NAND hardware gate by assign your H equal to H going to be equal to 1 or high true for your input, and for your output you assign your output to be low true. That's how you implement your AND gate by NAND gate. Okay, next, alternately, if you assign from the NAND gate table for high true input and high true output, okay, from that truth table. Now let's see if you assign low true at the inputs and high true at the output, what's going to happen? So for your input, because your input is the low 3, so you uh, need to relate your input ABC. That's going to be, instead of 0, this one going to be 1 1 1 1 0 0 0 0. Okay, now your output is the high true. So you get back to the NAND gate, the original one, truth table. So this one is going to be high, 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 and low, right? So that's why I have the last one to be low or 0. For the input to be low true and the output to be high true. So this one is actually what? It works like OR gate, right? You have output to be 0. If only your all input ABC equal to 0 or low. Okay, so this is how you use your NAND gate to implement the OR gate. Now let's see the first example, because we're going to move on. Now you probably know what does this mean, low true and high true. Giving logical variables A, B, and C, which are high true, we wish to draw a mixed logic diagram for function f equal to A prime BC or a complement BC, and using NAND gate hardware. This problem seems to be straightforward, but you will see some problems, and that we need to correct the problem or modify the problem later on. Okay, here, this is your what? AND gate, right? Because you need your AND gate, 3 input NAND gate. AND gate, sorry. And this one, we worked out that before, sorry. Okay, for this one is the actuator, the AND gate, by using our NAND gate array, because as the AND gate, you simply use the NAND gate, but your output is what? Your output is actually become low true, and your input is high true. So this is the symbol of NAND hardware as the AND gate. Okay, and you want to create the function f equal to A prime BC. So this is the represent input A high true, input B high true, dot H is mean high true, and input C is the high true, and this is your output is the F as the low true. And since you need the A prime or A complement, your slash here going to be represent the inverse of A, and then your A's turn out to be A prime, and you need also the half arrow for this one. That's the represent your convert from high true to below true. Okay, so that's what the meaning. And again, the slash does mean you do the complement, or change from A to be A prime, or you change the logic, for example, from 1 to be 0 and 0 to be 1. And for the half arrow here, that's the change high true to be low true. That's for the what would I say? Hold on a second, I'll show you this one just to be clear. I have it there somewhere. Okay. For the slash mark, actually I have it here. That's mean logical inversion. From A, when you put slash mark at the end of the wire, that's going to be a complement. For example, you have A to be 0 and 1, a complement going to be 1 and 0. And the problem viewer happen. This is the some conflicts. Okay, what I have here, this is the high true and this is the low true. The half arrow actually represents the bridging between logic and hardware. Okay, we come back to this one later on. For example here, this is your logic and this is your voltage. Okay, so when you put slash and the half arrow, what does this mean? For the slash, you have what? From A going to be a complement. For example, 0 going to be 1, right? For H, that's another thing. When you put half arrow, that's going to change high true to be low true, as you know I talk about it in the first page. But the voltage here, it's still the same. Now, if you start with the sorry, a low true, okay, you use the simple like this one, from low to high. Your slash is just go after the half arrow, but this one the half arrow goes there before the slash. So the half arrow going to change low true to be high true, and the slash going to change A to be a complement. Okay, this is for low voltage applied to the line, and this is high voltage applied to the line. But you will see later on that this doesn't change the voltage. Okay, you're talking about the voltage and you're talking about the logic. For A become A prime, you simply change the logic, right? From, for example, 0 to be 1 or 1 to be 0. But H, it just represent the logic, not the voltage. So it just show you either going to be high true or low true. And for the logic, A low true, and this one turned out to be A prime high true. For this one for high voltage and this one for a low voltage. You will see more examples just to be more clear. Okay, and we get back to this example. Okay, let's see. So you put the slash because you want A prime or a component, right? A complement, sorry. And then B is still the same, C is still the same. And this is actually your AND gate. So you already have the function A prime BC. Now you take a look at the truth table. You have our input A, B, C, and this is A prime. For your output, this is a 3-input AND gate. So your this you might get confused, but actually you need a low true for your output. So for A prime, B, and C, this is your actually AND gate, right? But your output need to be low true. So in that case, you have your output to be 1 when all inputs are 1. Okay, and this one I just compare to the this is high true compared to low true, so that's going to be opposite. That's mean or inverse, from 0 to be 1, or from 1 to be 0. Okay, now here comes the problem. The logic is correct, okay, because you already have the function A prime BC, but the truth value of input is wrong. We need to modify the circuit. Okay, why? Because when you talk about a circuit, this one seems to be conduct current, or you suppose you have nothing, between here. I mean, in the term of hardware or in term of circuit. So, if you have this one to be a 5 volt, and the other end of the wire is supposed to be 5 volt, right? It should have the same voltage. But it seems this one doesn't make sense because it looked like you put a 5 volt and this turned out to be 0, right? Because you have the complement. So we were working on the modification later on in the next example. Before we are doing the example, let's take a look at the voltage inverter. because we were introduce this one into your circuit to make it correct. The voltage inverter say that there's no logic. It doesn't change the logic. But by definition, for the inverter, when you have input to be 0, you want output, you expect output to be 1. Or input low, you expect output to be high. And for high input, you expect low output. Or when you're talking about the logic, this means you want to convert low true to be high true, or high true to be a low true. Okay, let's take a look. This is for high voltage input, and this one is for low voltage input. You take a look at this one. You have voltage. Because you say that this is the voltage inverter. Sorry, hold on a second. Okay, this is the for let's take a look at that voltage. Sorry, logic. This is the input A, high true. Of course, you want your output to be low true, right? So that's going to be opposite of A. That's straightforward. When A is 1 for high true, so for low true of A, that's going to be what, 0, right? This is for the voltage, high voltage input. Now for the low voltage input, you have your input to be 0 and your output going to be 5 volt. Okay, so you need to keep in mind this is the voltage inverter. It's something to do with the voltage. And this one is the same. A low true turn out to be A high true. This is the mixed logic symbol for inverter, and this is the alternate form. This is for high voltage input, from high to low, and this is from low voltage input. This is low to high. Okay. Now you will see that the apply mixed logic symbol. This one is the logical inversion. Okay, the slash. This is for logical inversion. That means you change the logic from 0 to be 1 and 1 to be 0. And for the half arrow, this is for the hardware. That's required for low true to high true, or high true to low true conversion. Okay, you need to separate two things. Let's take a look at this one. Okay, you know exactly that this is the high voltage input inverter, right? Is that correct? We have that one. Oh, sorry, this is for low voltage input inverter here. So you need to do a modification when you have a high true. Okay, and what we are doing here, this one is simply proving that by adding inverter, the wire, the same wire, for the hardware, if the voltage is high here, at the end of the wire, it need to be 5 volt as well. If you don't have this one, you have problem, right? In case you remove for your inverter, you see that this one going to be your this is a high true, and this one the slash represent a complement, and the half arrow is going to convert high true to be low true. So that's doesn't make sense, right? So by adding inverter, you can see that your output also become high as your input. That's for the hardware, okay, in the term of the voltage. So let's check it out. You have what? This one is the high. By putting the slash, this turned out to be a complement, and for the half arrow, this turned out to be low true. And now you go to another half arrow. This one, a complement, still be the same, but low true turn out to be your high true. Okay, and since I mentioned, before that the inverter doesn't do any logic conversion, so your A prime H still, become A prime H or A prime H true, show up at the output. Okay, this is just for example by adding the inverter that's going to make the input logic make sense. Now for a low true, this one has to be low as well, right? For your output. So that's balanced. So let's see how it works. And this is your high voltage input inverter, right? You check it out. This is a low true. By adding a half arrow, this turned out to be a high true, correct? And by adding another arrow, this turned out to be low true. And by adding the slash, this one going to be a complement. And this one, it just show up at the output of your inverter. So at this point, is there turn out to be a prime high true, right? And by adding another half arrow, this turned out to be a prime low true, okay, from high to low. So additional half arrows have been added to line identified with LT variables. So this is they talk about, as I explained. Now there's a rule. Properly constructed mixed logic diagram. The half arrows will always be balanced by balance on any given line segment. Okay, so that's why we add the inverter to the line segment to balance it. Okay, the logic. Oops, let's see where we're at. Okay, we will continue in the next YouTube series. Okay, I think I'm running out of time, and this is the page number 4, so we have 3 more pages to go. Okay, bye.